Okay, so let me give you a schematic way. So here's another theme that I will use over and over again. Don't use the word waste. Nature doesn't know the word waste. It always reuses waste. If you want to be sustainable, the equivalent is no waste. Every waste should be turned into a resource. That's the only way to make things economical. Waste, people think, oh, 我要花钱, I have to spend money to. But if it becomes a resource, you can earn money. Then people would do it. If you have to spend money, everybody's reluctant to do it. Okay, so try to turn waste into a resource, and that's what this graphite thorium reactor or lifter or two-fluid molten salt breeder reactor. So you start with nuclear waste from light water reactors. So you have uranium-238, uranium-235 that didn't get transformed or didn't burn. So you take that out or separate it chemically, and you give it to people who want to build fast reactor, the integral fast reactor, or Bill Gates who wants to build the traveling wave reactor. They can use it. The leftover plutonium and higher actinides, you can use the process of pyroprocessing and use that as a fuel. That is a fuel, all right? It has excess neutrons, so if you surround that with thorium in a form of a salt, the excess neutrons will come out of the core and turn the thorium into uranium-233. Very dilute, so how do you get it out? Well, this is a liquid, so if you take some portion of it and you add fluorine gas or hydrogen fluoride, there's a process called fluoride volatility where uranium F6, not uranium F4, turns from a liquid into a gas. A gas and a liquid will just bubble up, will just separate by itself. You turn it back into a liquid, you put it into the core, and now you have what's a breeder reactor. So you use the waste, it's like a match, like a pilot light, you get it started, but once you get it started, it becomes self-sustaining, okay? So that's a breeder reactor, this is a converter reactor. Now, the difficult things with fission products, of course, you have to also get out. You have to do it by chemistry. And this was the argument between Fermi, who pushed the sodium reactor, and Wigner, two Nobel Prize winning physicists. Wigner was a Nobel Prize winning physicist, but his undergraduate degree was chemical engineering. So he knew, unlike all these physicists who think they're so smart, okay, but very rarely know any chemistry, okay? He knew if you want to do chemistry, the best phase to do it in is a liquid, not a solid. Solid, you have to melt it into a liquid, and you have to refabricate. He knew if you have a liquid, you can do continuous processing so that removing the fission products becomes relatively easy. Not easy, but relatively easy. So that was the great insight of Oak Ridge, which was run by a protege at that time of Wigner's, which was Eugene Wigner. So this is the graphitic core module that we got SGL polycarbon to build for us. S stands for Siemens, G stands for graphite, and L is a company in Southern California that they took over. Everybody takes over companies and make what's on sale. Okay, you want to buy it, you can get. So they built this for us. This is nuclear grade graphite where we cross drill holes so that the channels don't cross. So here we send fuel salt. When it meets the bottom, it turns up, it goes back up. So it just circulates as a pump, as a cycle. So we don't let it do anything other than transfer heat to the blanket salt, which carries the thorium. As it's carried into this reaction zone, it's irradiated with neutrons, so you also turned it into new fuel, which then you use chemistry to put into the fuel salt channels. So you need nuts and bolts, and you need things that conceal these things. And this is carbon composites, okay? I won't go into the details. A group from Caltech, based in Caltech, has made some YouTube videos of this thing, and you can go on to YouTube, raw science, and click on this thing. Anyway, here's the basic points. Because you're talking about fluids, it's possible to safely extract uranium-233, and you always make some uranium-232, which is proliferation resistant for reasons I won't talk about, in this pool. This is surrounded by a large pool, which carries a blanket salt, bifluoride volatility. Now, how do you get out all of the fission products? Fission products 很讨厌啊. It's everywhere. Left-hand side of the periodic table, right-hand side of the periodic, middle of the periodic table. If you have to extract each one by one, it's 很讨厌. Okay? So it's a very simple way to get rid of them. Leave them behind. Extract the solvent. Okay? Vacuum distill the solvent after you've taken out. Then you just leave behind. That's the ultimate waste. Okay? Even that's not a waste. Those of you who do nuclear medicine, nuclear batteries, know we shouldn't be calling that stuff waste. It's useful. If you have a light that you don't trust to go out, okay, or a pump that you need to turn on, don't use a chemical battery like Fukushima. You should use nuclear batteries. Okay? Exit sign, that's powered by tritium. Did you know that? Okay? Lighthouses in the Arctic cannot go out. That's powered by strontium-90. So these are resources that we should make use of once we get over this irrational fear of low-level radiation. Okay, so it's safe. There's another aspect which convinced me as an astrophysicist. You see, when I went to Tsinghua Daxue, I had to understand what people like him did. And they're very vocal. They insist I understand what they did. So I had to read up on different kinds of reactors so I could talk, sensibly to them. And what I discovered, what this reactor does, why it can regulate itself, I said, oh, this is ultimate in safety. Why? Because it's self-regulating. It's what the experts call load following. Why is it load following? Well, remember I said you extract the heat by pumping on the blanket salt. If I pump harder, I'm cooling it down, right? When it cools, it contracts like any liquid, goes into the core and speeds up the rate of nuclear reaction. So when you want power, it gives you more power. If you want less power, you pump less hot. It gets hotter. It expands out. Reactions go slow. That's exactly how the sun works. Okay, I'm an astrophysicist. You have to take my word. Exactly how the sun works. There's no operator running the sun, yet you can depend on the sun tomorrow being like it was today, if you can see it. Okay? It is safe, just like the sun is safe. Okay? So, how much footprint does it have? Well, nuclear power, this is something that people don't realize, is so much more than nuclear energy. It's millions of times more powerful than any form of chemical energy, which is 1,000,000 times more powerful than most forms of mechanical energy. Right? That's why fossil fuels beats wind. You put in a few liters of gasoline, 车子可以动, right? 跑得很快, right? Think about powering it with wind turbine. Very difficult. Nuclear energy is 1,000,000 times more than that. So what is a footprint? It's the tip of your little finger. Okay, that's your environmental footprint per person. It's not zero waste, but it's practically zero